Fibers are a really cool concept that enables some powerful functionality like concurrent rendering in React. But what actually are they and how do they work? Don't worry, I'm here to explain, and stick around to the end where I'll show you how to build a basic custom fiber runtime completely from scratch. First though, what actually is a fiber or a fiber runtime? This one's a little complex, so let's look at a diagram. The most basic definition of a fiber is a non-blocking unit of execution. But what do either of those words mean? Let's start with the unit of execution. We can simply describe that as a program, but what actually is a program? The definition I'm going to use for a program is a set of lazily evaluated immutable steps. But again, what do those two words mean? Immutable is a slightly easier one to understand conceptually. It basically means that things are unchanging. If you consider the steps of a program like the lines of a script, they're not swapping around at runtime, right? Like they are what they are when we run the script. And lazy just means not doing work until it's needed. And there's some kind of higher order use cases for this, but this is actually how all programs work, right? Like we go line by line and we don't like skip lines and start processing other stuff. We just do it when it's the next step to do. Let's take a look at a short example. So here we have a simple program, right? This is a set of lazily evaluated immutable steps. The steps are our lines of code, and when we give them to Node, they're immutable, right? They're unchanging. And these steps are evaluated lazily, right? Like if we run this code, see, we get the first console log and then the second console log. But if we throw an error halfway through, we never get the second console log because we kind of went line by line. And when there was an error, we stopped evaluating. Now, this definition of a program is very high level, right? Our entire kind of JavaScript file and program. But the definition I used earlier, a set of lazily evaluated immutable steps, can actually be applied to things within our language itself, right? Consider a function, for instance. So here I defined a function called foo, which does the same thing as before. And just like our other program, functions are lazily evaluated, right? If we run this code but never call the function, they never get called. And if we run this function, but we error halfway through, right? Even within the function, it's lazily evaluated. And now we get the error. And of course, functions are immutable. You can change properties of the function object, but the actual source code cannot be modified after you define the function. Now back to the diagram, we only have one part left, non-blocking. What does that mean? I defined it here as occasionally yields somehow. To understand what this means, let's start by looking at what a blocking function is. In JavaScript, all synchronous functions are blocking. So in this example, we declare a variable x, and then we have a synchronous function foo, which logs x at the start and end, and then we have bar, which logs at the start and end, incrementing in between. And so then we call foo, and then we call bar. And when we run this code, you get pretty much what you expect. Foo start, foo end, bar start, bar end. Now, in JavaScript, the easiest way to get a non-blocking function is to make it asynchronous. So let's see what that looks like. So let's make foo non-blocking and see what effect that has. I'm going to make foo an async function, and then in between start and end, we're just going to await a new promise that immediately resolves. And so now if we run it again, we'll see that bar has actually inserted itself in the middle of foo's execution. And how is this possible? Again, this is where the yielding comes in. Foo starts, and then when we reach an await point, it yields back control to the JavaScript runtime, which allows something else to run, in this case, bar. So foo starts, it yields, bar runs, and then it goes back to continue foo. And this pattern of having two different things running at the same time is called multitasking, but there's two different approaches, so let's break those down. The first approach is called cooperative multitasking, and this is how JavaScript works. In JavaScript, there's only one main thread, and so whatever is running on that main thread has to finish or yield control somehow for something else to run. And so the way this usually looks like is either code hits an await point or the stack completely empties. And tasks in this model are just callbacks in a queue, right? As our function goes along, we initiate these callbacks, which end up in this callback queue. And when the stack empties, the runtime pulls the next thing off the callback queue and continues execution. This is called cooperative because the functions itself have to yield, right? Everything is synchronous until you hit that await point, and there's no possible way to yield outside of explicitly calling await. The alternative here is preemptive multitasking, and you can think of the preemptive as instead of waiting for a function to yield, something else preemptively stops it. And so in this model, each separate task runs as if it's the only thing running. And occasionally it gets stopped by some external scheduler. So this is how operating systems work, right? You have a bunch of different processes, like different applications, and they all run as if they're the only thing running. And your operating system steps in and says, okay, now this one gets to run and this one gets to run, and eventually they all get to run. But the operating system is the one that decides when execution gets stopped and resumed. The other key thing in this model is that because tasks can be stopped and resumed at any time, they have to be stateful, right? They have to be able to store where they were when they got stopped so that when they get resumed, they can just pick back up. And so in an operating system context, each program has its own stack, and the stack gets saved to memory whenever a context switch happens. And so when the program gets run again, it just picks back up from its stack where it left off. And so the core idea of a fiber runtime is that we can have purely synchronous work that can be paused and resumed. That's the preemptive model, but inside JavaScript where the only option is a cooperative model. Why could this be useful? Well, imagine we have a big synchronous function that takes a long time to resolve. If we just call a synchronous function, it will completely block the main thread. What we really want a way is to kind of split that work into chunks and still complete it, but give a bunch of opportunities for other asynchronous stuff to run. The best example of this, like I mentioned at the beginning, is concurrent rendering in React. First, let's take a look at how this worked pre-React 18 with non-concurrent rendering. Rendering a React tree is a purely synchronous operation, which just consists of kind of recursively calling all of the components. But if you have a big enough component tree, this can take a significant time to resolve. And again, because JavaScript is single-threaded, for that time that we block the main thread, any event handlers or state updates that happen during that time get pushed until the main thread yields, which is at the end of that big successive render. And the result of this would mean that your application could feel really unresponsive, right? You would click and you'd expect something to happen, but React was finishing a big synchronous render, and so the click event wouldn't actually go through until a little bit later. And the solution introduced in React 18 with concurrent rendering is to make that big synchronous operation non-blocking using a fiber model. And the idea is that because it's non-blocking, even though it's purely synchronous, it will occasionally yield. And when it yields, there's chances for these state updates or events to trigger, and your application feels a lot more responsive. And while this is really cool, it still doesn't answer the question where in JavaScript, where we have this cooperative multitasking model, how do we achieve a preemptive multitasking model, which is required for a fiber implementation? And so the way we do this is actually pretty cool. We start by creating our own language inside JavaScript called a DSL, or domain-specific language. And we write our programs in this language. And these consist of like a big tree of objects which contain all of the steps of our program. Then we create an interpreter, also in JavaScript, which traverses that tree and executes each step one at a time. And so then in this interpreter's main loop, we can either internally or externally, it can just choose not to execute the next step and instead save its state and kind of schedule asynchronously to pick back up and resume. And what this does is the kind of execution of steps kind of occasionally yields back up and allows other stuff to run. So I know that was a lot of explanation, but hopefully that will give you a strong foundation to kind of conceptually understand what's going on when we implement this from scratch. So let's get to that. Before we get started, I just want to show you what the end result is going to look like. So in this example, I have two different intervals. So I have one, which is an async interval, which is basically equivalent to while true, console.log, and then await the timeout. And so this is going to kind of do this interval asynchronously, right? And now for the spin interval, this is a purely synchronous interval. So we basically declare a variable and then count to a really high number and then log out and then keep counting. And so this counting is purely synchronous, right? It's its own, there's nothing async happening here. And so here I create three fibers. So there's two that are doing these like synchronous, just like spin counting intervals, and one that's async. And you'll see that when I run it, because of the like non-blocking preemptive multitasking that's happening in our fiber runtime, all of these are going to run at the exact same time. So this one's going to log 1, this one's going to log 2, and this one's going to log 3. And if I go ahead and I run this, you'll see that 3 is running, 1 is running, 2 gets in there. And so all these are running at the exact same time, which is super, super cool. So let's check out how that works. The implementation starts by defining our DSL. And this is all going to be around one core type, which I'm going to call IO. So we're going to start by defining this type called IoT. And the first thing an IoT could be is a sync op. And so a sync op represents a step in our program which computes a value synchronously. And so we can create this as a class. And so the class is going to have a tag called sync op, so we know what value this type is. And the constructor is going to take one value, which is just a function that returns that type. And so then we can create a nice little wrapper around the constructor called just a function called sync, which takes the same arguments and calls the class constructor internally. The next operation we're going to need is a async op. And so the async op is actually going to be very similar, except it's going to be asynchronous, right? It's going to return a promise t instead of a t. And so the way our programs are going to look is we are going to build up our programs. So here's like the most basic program, just synchronous. And we can have a asynchronous function, and so these programs obviously are very primitive. What we really need is a way to combine two operations. And so for that, we're going to add a new step called chain. And so we're going to add this to our IO type, and we're going to call it chain T. And so our class for chain is going to look a little bit different because there's some kind of weird TypeScript stuff we have to get around, which I'll show you why in a second. And so what we really want is a type that allows us to take the value of the previous IO and return a new IO. So for example, a program could look like here, and let's just define a constructor function for this. We could say chain, we could say promise dot. So now our IO is starting to look a bit more like a real program, right? We can define like a first step and a second step, which depends on the first step. And you'll notice that this entire program is still of type IO, right? We've created this structure, which kind of is a value that describes all these different steps of the program, right? And you can kind of start to see where this is going. And so a small problem right now is that our chain type only operates on a single type, right? Like everything here is a number, but to have useful programs, we kind of need to operate on more than one type. And so, for example, if we change this from a number to a string, we now get a type error. And so we have to kind of redefine our chain to take two types, right? A and B. And so it's going to start with an IO of A and take a function from A to an IO of B. And then the whole kind of result will be an IO B. And so we can kind of guarantee this types on this function, but the actual implementation, we basically have to lie to TypeScript and kind of tell it we know what we're doing. So these are all going to become unknowns. So this is going to be unknown, and this is all going to be unknown. And so then we can just say TypeScript, we know what we're doing, and everything's okay. So now we can start to build up, actually, with just these three, we can build up basically any program. So let's see what that might look like. So take a look at this, which I just implemented, and it's starting to look a bit more nice, right? Like we're fetching from a endpoint, and then we're chaining that with another chain, which does an async operation to get the text. And then we use that text and do a sync operation to log it out. And so you can start to see how with just these simple building blocks, we can build these very large programs. But how do we actually run them? That's where the fiber comes in. And so our interpreter is actually just also a class. It's going to be called a fiber. And so our fiber is going to let's start by defining the constructor. And our constructor is going to take a starting operation that is type IOT. And this is the program that we're going to execute. And so we're going to store this in a variable called the current op. And this is going to be a IO of any. And there's going to be quite a lot of like TypeScript any's and unknowns here, but basically we do all the type checking in the constructors of our DSL. And so when we're interpreting the DSL, we basically just assume that everything works. So in our constructor, we're going to start by assigning the current op to the starting op. And so the main loop of our fiber is going to basically be, we're going to have a function called run. And this is going to return a promise T. And basically the way it's going to look is we're going to, while true, switch on this.currentOp.tag, and you'll start to see SuperMaven do some stuff. But basically, right, we're going to have a big statement, and we're just going to go through the operations and do some kind of logic for each different possible thing it could be. And so actually with this current implementation, we don't do the non-blocking at all. So let's see what that looks like. And so we're going to start by creating a private function called should yield. And this is going to return a Boolean. And so you'll see, here's our implementation. We're going to create a new instance property called opCount. And what this represents is the number of operations we've executed since we've last yielded. And basically, we're just going to increment this on every operation. And once it gets greater than 10, we're going to say, yes, you should yield. And so then instead of while true, we're going to say, while this dot should yield. And then if that fails, and so then if we should yield, how do we schedule to pick back up later? Well, we can use a callback, right? We can say set immediate and this dot run. And so what this is going to do is we're going to execute 10 steps. And then after 10 steps, we're going to say, yes, we should yield. And so we're going to set off this callback to continue our run loop. But because that callback is asynchronous, we yield back to the runtime and other things get the chance to run. And then when that callback gets run again, our run loop continues for another 10 steps. And so here you can start to see how we get this non-blocking execution. So to test our program, let's actually see what this looks like, right? So we're going to say const fiber equals new fiber real program, and then await fiber.run. And so if we try to run this right now, obviously we're going to get a bit of an error. Actually, nothing's going to happen, but we can fix that. So the first error is we're not actually returning a promise right now. And so we're going to create a new property called hasExited, as well as a property called onDone, which is going to be a function we're going to run on completion. And so now we're going to move this function into a kind of internal function called run underscore. And the function we expose externally. And so the first thing it's going to do is create the promise that we're going to return. And we're actually going to use the new promise.withResolvers. And so then from that, we can get promise and resolve. And so then we can assign resolve to our onDone function, which means that when this fiber completes, it's going to resolve that promise with the value. And then we can start our run loop and finally return the promise. And so now run, this is actually going to be just void. And if we run it again, let's see what happens. Okay, it's still just spinning. And so now we can actually start implementing each of these different cases. And so the first one is actually pretty simple, which is sync-op. So first we're going to get the sync-op, which is the current operation. And then remember, sync-op is just an object with a property called op, which is a synchronous function to get the next value. And so we're going to get that value by calling that function and assign it to a result. And then we're going to call this.advance with the result. And so we haven't actually implemented that. So let's start. And so advance is going to take any value and just be void. And so the first thing we're going to do is say if this.hasExited, we're going to this.onDone with the value. And otherwise, we can not worry about that for now. And so if you think about what's happening, let's actually create just a simpler program. And so we're going to create const program equals here. And if we run this program, everything should work now. Oh, okay, and just some small errors from me. So first, we need to make sure that we're checking not if this.should yield, right? This.should yield returns true if we should yield, so we should only continue our run loop if we should not yield. And then we also need to do this check when we schedule our work to continue asynchronously, right? We only want to do that if, again, we have not continued. And then finally, we want to do this onDone if we have not already exited. And so now if we do that and we run it, we just get our execution, which is pretty cool. Again, very simple for now, right? But this is progress. And so next, from there, implementing async op is actually not that complex. We start by getting the async operation, and then we call it, but this returns a promise. And so we use .then on the promise to give it a callback when the promise completes. And basically what we do is we say, okay, when it's done, like with the synchronous function, we just immediately call this.advance. But with the asynchronous function, we're saying when that promise completes, then call this.advance. And after that, where before we would break, here we can actually just return, right? Because if you think about it, we call this.advance, which is for now always finishes the fiber, but eventually it's going to do some other stuff. And so we probably want to continue the loop, right? So break just kind of moves on to continue the loop. But with this asynchronous operation, we know that there's no reason to keep going through our run loop, right? Like we've set up this callback to continue it at some point, but for now we can just completely exit from the function. And so that's why we say return. And so now the real magic is in chain, right? How do we kind of continue these successive operations? And so the way this is going to work is we're going to create a new property called a continuation stack. And this is going to be an array of any. And what this is going to be is every time we encounter a chain, right? A chain consists of the previous operation and a function to get the next operation. So when we encounter this, we're going to take that function and place it on the continuation stack, and then set that operation to our current operation and go around our loop. And so then in our advance function, we're going to add some logic where previously we always just exited. Now, first we're going to check if there's a continuation on the continuation stack. We're going to pull that off, give the result, right? Because in the advance function, we have the result from the previous operation, and call that and get the next operation. So let's implement that now. And so here we're going to start by getting our chain op from this .current op, and then we're going to set the chain op.io to the fiber's current IO, and then push the chain op onto the stack. And so you might be wondering why we push the entire chain op onto the stack instead of just the function. And basically, eventually we'll want to add other things besides this chain op onto the stack. And we need some way to figure out what it is when we pull it off. And it's really easy to use the fact that we know it's a class to say like continuation stack.pop is like instance of chain, and then we know it's a chain. Where if we just had the function, obviously it's a lot harder to tell there. So now let's update our implementation in advance. And so we can start by first getting the continuation off the stack. And then we can say if there's a continuation, and if continuation is an instance of chain, then again, we have access to the result of the previous operation and the function to get the next operation. And so we do just that. We say this.current op equals the function given the value. And if I spell this right, continuation. And then we just need to put this other code in an else block, and everything actually will work. So now we can get rid of this kind of stupid program, and we have our real program, right? It has chained operations, synchronous operations, asynchronous operations. And if we run it, we can see that it actually works. It fetched that to do, it logged it out. And believe it or not, that's actually the entire implementation. But our programs are actually really simple right now, right? Like we aren't even hitting the 10-step kind of point where we yield. So now let's create some larger programs where we can actually see that preemptive multitasking happening. And to do that, we're going to use generators. And generators are actually a really common pattern in effect, but the implementation is actually pretty simple. To start, we're going to find a new class called a gen. And a gen is going to have a tag, and it's going to take a function that returns a generator that takes type T's and eventually returns an IO. And the types here are actually not going to be as great. If you want to have like a full amazing types with the generators, there's a lot of kind of crazy stuff to do, but we're going to limit it just so it's simple, where within a generator, you only have like one type available. Like every operation is going to use the same type. And so the way it's going to look, and so we can create a new function called gen, and then we just need to add this to our IO type. And so here I just brought back the two examples from the beginning because they're pretty good at showing what's going on. So we create a new kind of function that returns an IO. So generators are really useful because the alternative to generators is a lot of functions and a lot of deeply nested functions. But if you think about a generator and chain, they're actually like very, very similar, right? Like chain takes a previous operation and a function to continue that operation. And a generator, you keep calling next, and it gives you values, and then you call next again with the result of that value, right? So in this generator, we yield a sync, right? And this is an IO. And then the type we get back, const I, right? This is the result of that IO. And so if you think about, like, we call next, and next gives us the IO. And then when we call the generator again, if you don't know, like the yield expression evaluates to the value you call next with the next time you call that generator. And so in that way, we can get this like chained operations, but with a lot nicer syntax. And so the way this looks like in practice, right, is we have an async interval. And so it's a generator function, and we say while true, and we yield a synchronous operation where we console.log the ID that's passed. And then we yield an async operation, which just awaits a promise tied to a set timeout. And so our spin interval is also a generator, but it basically goes in a while true loop and yields a synchronous operation that kind of increments this number. And then occasionally when the number hits a certain count, it's going to yield a synchronous operation that hits this console log. And so now we can go ahead and run 3 different fibers, 2 with the sync interval and 1 with the sync interval. And if we go ahead and run this right now, nothing's going to happen because we haven't implemented the generator logic yet. So it's actually not that difficult. The first thing we're going to do is in our switch statement, add a new case for gen. And we're going to go ahead and get the gen op from this .current op. And then, and then we're going to get the generator by calling genop.gen, because remember, it takes a function that returns a generator. So by calling that function, we get the generator. And so then the first thing we need to do is, remember, our kind of thing is structured around setting this .current op to the next operation. And so to kind of get that started, we have to call .next one time. So we're going to call .next. And if it's done, just by chance, like the first operation is done, then we can actually just go ahead and advance. Otherwise, we're going to push the generator onto the continuation stack and set this .current op to the next value. And so again, this is very similar to chain, but we just need to have some slightly different logic. So in our advanced function, when we pull something off the stack, before it could only possibly be a chain, but now we can say if it's not a chain, then we know it's a generator, right? And so what we can do is take that continuation and call .next on it, because the continuation is the generator and it's expecting us to return the value of that IO, which we now have because we're in advance. And then we can do the same logic as before, where if we're done, we can advance with that value and finish or go on to the previous completion. Otherwise, we're going to push it back onto the stack and set the current op to the new next value. And that's actually all it takes. So if we go ahead and run this, you'll see we get the 3 different intervals kind of interleaving. And so let's just recap what's happening here, because it's actually really cool. We create 3 different fibers. So 2 are these kind of synchronous spin intervals, and 1 is this asynchronous interval. And we call run on all of them. And all of them are getting run kind of interleaved, right? And the way this is working is each one, the generators they're all in a while true loop, right? They're all yielding just infinite steps forever. And so within each fiber, it's in this run loop, this switch statement, right? This while switch forever. But after 10 operations, then this that should yield, right? Which increments each operation, and after 10, it yields true. Then after it yields true, we go out of this while statement and we kind of set this asynchronous continue, right? So the state of the fiber is stored in the continuation stack and the current operation. And so because it's in there, we can just say, okay, we're going to yield for now and schedule the continuation to happen asynchronously. And so then the next fiber gets a chance to run. And so it's going to run through 10 operations, and then it's going to yield and schedule itself. And then the next fiber is going to run in 10 operations, and then all of them have run. And so then the runtime is like, okay, I have nothing left to do. So it pulls the first callback off the queue, and that one says, okay, continue running the first fiber. And this goes on forever and ever. And so this is how we're able to have these fibers, each of which don't have an explicit yield point, right? They just have a series of steps, and they all kind of act like they're the only one running. And so in that way, we have these 3 different execution contexts, right, that all kind of occasionally yield, and in that way, they're all able to run at the same time. And so again, to bring it back to the React example, you can see how if we do the React rendering in a fiber and we kind of yield over time, there's a bunch of opportunities for other stuff to run, right? Like just how these fibers kind of give opportunities for the other fibers to run. If we're rendering and kind of occasionally yielding and giving opportunities for like state updates or event handlers to run, right? It's the same thing, which is really, really cool. And so that's really all there is to it. I'm going to put all the code in the description below. You should definitely go check it out, play around with it. If you're looking for some ideas on how to expand on this kind of topic, you can add more operations. You can add a external scheduler instead of the scheduler kind of being very simple and built in. I just made a video about structured concurrency. And so you can kind of implement that, like make a new operation that's called fork that makes a new fiber, and that the current fiber stores its like children that it forks. And then you can add interruption. And so on interruption, it recursively interrupts all of its children. So this topic is really one of my favorite programming concepts right now. I really love it. And so you should definitely, if you have any questions or ideas or anything, leave them in the comments below. I'll definitely be looking. And other than that, thank you so much for watching, and I'll see you next time. Bye.